G'day, Glenn Morris here from the Smart Energy Lab. And today in the lab, I've got Brendan Sauer from Discover Energy Systems. Now, Brendan, I've known about Discover for quite a while. I've had some of their products before, but they've been completely different. So today we're going to be looking at something a bit more racky mounted.
A little more racky, you could say that. Yeah, this is our new AES rack mount. So
Yep.
An evolution of our smarts and our BMS in a more palatable form factor.
Yeah, cool. Now, before we dive into the product itself, for those who don't know about Discover, tell me, who are they? Where did they start?
Discover, you could trace its roots back to a simple automotive battery shop in the middle of Canada that grew from that one shop to many locations to coast battery distribution in Canada and the US, and then began to seek its foray into manufacturing of traction lead batteries.
Yes, I imagine 1949, it wasn't lithium.
Yeah, of course. And we picked up our lithium journey 2013.
Wow, okay, all right. And the lithium journey has actually been quite broad. I mean, I've just looked at the product list on your website. You make a lot of different products.
Yeah, so primarily it was a team of mechatronics engineers, so passionate about hardware and firmware and software, enjoyed mechanical as well. There's always been a large solar team within Discover, but we still have those roots of motive mobile, heavy construction equipment, RV caravan type
So just
batteries.
battery only.
So so we've got products for equipment and machinery, and you've also got the solar product. So if you look at some of our older blocks, the AES 4248, a big, massive battery.
Yeah,
it's as ugly as it is. It was designed for traction applications and motive equipment.
Yeah.
Just so happened to have a great BMS, and it worked well with heavy transformer-based inverters.
That must weigh like nearly 100 kilos, that thing.
It's 200 pounds. So
yeah, something like that. Because I've had to move it a few times. At least it's got those nice little handles
it's
on
a
it.
two-man lift for sure.
Yeah. Oh, that's good. So here we've got this new rack-mounted battery. So this is what's it called? The AES rack?
AES rack mount.
Yep. So it's your standard 19-inch rack.
Yep.
It's 3RU.
3U.
Not 3U. RU. Yep. And it's got these funny little stands attached to it. What's this all about?
So there's multiple configurations you can deploy this in. If you have your own rack, you can go ahead and slide the module in. Now, these are our quick stack racks. So it allows you to actually build a system without having a rack or an enclosure.
So you can just stack them.
Yes, yeah.
Right. And I notice it's got space underneath here. What's that for?
Both thermal, so we will need a bit of airflow if you're really stressing these batteries, as well as we've got this combiner box here. So this allows you to parallel the batteries and have your home run cables to your power electronics. And it just provides a quick, easy installation, route the cables underneath, attach to the front, and the whole installation might take you 30 minutes.
So no daisy chaining of one battery to the next. You go back to the combiner box.
No daisy chaining. We're always a fan of big power, high current.
Yep.
And daisy chaining, not really set up for that.
Now you mentioned high current. What sort of discharge current can you get out of these?
Standard, so 1C charge, 1C discharge. We do have peak C rates of 2C.
So what sort of peak current can you get out of these?
These will surge to 2C, so that's 200 amps. Standard charge and discharge is 1C in, 1C out, so 100 amps.
Wow, it's pretty awesome, especially when you've got a stack of these. Really quite interested to see that the combiner box comes with pre-terminated cables, so they're already the right length. And you've got some sort of connector on the end there?
Yeah, so these come with an Amphenol connector. So just plug and play, and it's pre-populated both to save time. And when we're doing our safety and failure mode analysis, some of the highest numbers are actually populating these combiner boxes. So if someone doesn't do proper torque, it can generate a lot of heat, a lot of issues. So in our safety reviews, it's actually the safest thing to do to send a pre-pop.
Right. So effectively, the installer's just plugging things in, which you can't get wrong, right?
Yeah.
It just goes click.
Exactly.
You've done the job. So you don't have to worry about torque settings. That's already been done in the combiner box.
Correct.
Off camera, we were talking about the length of the leads and the fact that they provide some dampening. Now, what's that about?
So if you take a step back in history to lead acid and you look how the batteries are constructed, you've got lots of plates, negative, positive. And if you looked at a capacitor, you might see it also looks like that. So there's a capacitive component of lead acid batteries that will take in ripple and kind of equalize that voltage. You step over to lithium, very low in total impedance, and it doesn't have that passive component either.
Oh, I never thought about this. The lead acid battery actually got built-in dampening.
Absolutely. So
right.
if you look at older inverters as well, you'll notice there's a large AC component
Yes.
that they're putting out. And lithium, you can see it. If your current acquisition's fast enough, you'll see the BMS
Yes.
pick up the AC component. So by having a little bit of a lengthy cable, it acts as a bit of a dampener. So it'll encourage the batteries to more equally share the current of the system.
Right. So that's the other issue is you might think just because they're all connected to a common DC bus, they're all going to charge and discharge at the same rate. But when you've got slight impedance differences inside the cells, unless you have that dampening, that will be magnified. And so you'll have some, batteries that are getting more and others getting less.
Absolutely.
That's a really interesting point. So you're kind of like solving a lot of those accidental construction problems, which is making up your own cables, not getting them the right length,
Yep.
not providing enough dampening. And you can combine how many on the combiner box?
So the combiner box is configured for 6. There are ways to expand that to 8.
Yep.
The communications for these batteries will actually be able to stack up to 36 batteries with closed loop communications or a managed BMS configurations.
So multiple combiner boxes.
You could do multiple combiner boxes.
So a stack of 5 or 6, did you say?
6.
6. Okay, stack 6 up to a total of 36.
36.
Whoa.
Now
okay.
that might be a different deployment, so you may choose not to use a quick stack rack. So you might go back to a standard rack with bus bar.
Yep. And then, of course, you'll have a backplane bus bar probably that all the combiner boxes are joining onto. Is that how it
Combiner
works?
of combiner.
A combiner of combiner, yeah. Now, does a combiner box provide any other functionality apart from combining?
So each battery is fused internally, and then we have a disconnect up front. And really, the disconnect is more for convenience when you're servicing the product.
Yeah. So turning off the combiner box will turn off the 6 batteries connected to it.
It won't. The batteries remain on, but it'll disconnect your power electronics from the batteries themselves.
Right. So you said there's fusing on each battery. Is that the circuit breaker on the front here? Or?
That's inside the combiner box.
Oh, right.
So
you've also got a
We've
breaker
also
on the
got a
front.
breaker on the front.
Yeah.
If you flip it over, the BMS will, I believe it's in the off state now, so it tells you, hey, my breaker's off.
Right.
So we've got a breaker on the front that breaks the positive negative pole, and that was derived out of Australian requirements, actually. Don't need it in North America at this time. And then there's also 2 internal contactors in series.
Right. Now, the other thing we were talking about off camera was about the nature of a BMS in terms of the things it has to achieve to look after a battery. What are some of the features that the BMS has in here? Which is, of course, one of your sort of pet projects, really.
Yeah. That's the reason I got into this industry. It's really the BMS and the
Yep.
firmware. So primarily, a battery management system's first and most important function is just to protect those cells. Mm-hmm. Let's make sure we're operating within our operating envelope. Voltage, temperature, current. So the first thing we're always looking for is just keeping that voltage within spec. And if you've got a closed loop system, we can control the inverter. We're actively keeping that voltage down below the thresholds where we need to open.
What's a closed loop system?
A closed loop system is where the batteries through our link to gateway here, the batteries are asking and dictating to the inverter what our charge voltages are, how much current we can take at that time, where we should terminate discharge. So we'll reach out to the inverter or power electronics and say, only give us this much or only take this much.
So the loop is between the charging source and the battery.
Yes, yeah.
And being closed meaning that it's a two-way communication.
It's a feedback loop. So
Yep.
I say, give me 50 volts. I see you're giving me 49. Why don't you give me 100 millivolts more? Or,
Wow.
So that closed loop,
Yep.
it's just an active discussion.
Yeah. And what's the purpose of having that closed loop?
So when you're in an open loop configuration or what do we call it here in Australia?
Self-managed?
Self-managed. We always say you should derate the operating specs. Mm-hmm. Yeah, so we've got 100 amp hour prismatic cells, lithium iron phosphate chemistry,
Yep.
and they're laser welded together. So really nice, robust connection.
Yep. And then you've got some internal battery management system.
Yep. So there's also heating. I forgot to mention. So there's heating elements.
I was going to come and ask about that because that's pretty novel. I mean, apart from cars, I haven't really seen it in energy storage devices.
It's starting becoming an expectation, and I was a skeptic at first, but through testing and demonstration, if used properly in the right enclosures, it does work. So you get your cells, your heating elements, and then you get to the front where all the power electronics are, and that's our 4th generation BMS.
Yeah. So you got some software that talks to the links too.
Yeah, so this is our Link Access software. That's where you can configure and set up your system, as well as check in from time to time, see how things are going. This is also how you download data logs from the battery, how you push firmware to the whole system. So we'll use Link Access.
So you just connect it via USB cable?
This is just a USB cable, yeah.
Right. And what sort of diagnostics could you get out of this through the links to the battery?
So very extensive. I mean, there's just your simple review of, hey, what's my state of charge? What's the voltage at?
So this is like the hero screen. Like
The hero screen, exactly.
Yeah.
Just your basics, your fundamentals. I can see right now. So another important one is our reference voltage. So if Link was hooked up to a charge source, it's requesting 54.4 volts right now.
Right. So that's the target it wants to achieve.
Yeah, and you'll see that start to float around and move throughout the charge. Current, battery temperature, our relay positions. And also you can hop in here and force them. So you might have an individual who, they don't know how the system works, but they know they need to turn the generator on.
Yeah.
Call home. All right, open up link access. Just force relay 1 on.
Right.
Or off. So I realize.
Now you've also got
earlier.
state of charge on the app, but what I really like, you've got state of charge lights on the link.
Yeah, a quick visual indication. So
Yeah.
5 LEDs. It'll also tell you if it's charging. So it starts to flash a little bit.
Okay. Right. So it gives you a little bit of information about charging. Now, in terms of SOC, the state of charge, it's doing it on the whole pack, of course.
Yes.
So this communicates with all of the batteries through what?
Through the
red
CAN
cable?
port.
So it's
So
got-
through a link port, that's a CAN bus.
So you've got in and out CAN ports on the front of the battery.
Yep.
And does it include the combiner box?
The combiner box has an in and out port, but it's just there for convenience.
Oh, okay.
So there's no real electronics inside this box.
Right. So it's to pass through.
Yeah.
Yeah. Oh, okay, cool. And let's get down to some more details. So say, you're doing a new installation and you want to make sure you've kind of done it properly. How does the link help?
There's likely 2 ways you could circle back to verify your installation. So one is, in the moment, you can hop in and you can see the current. So if you've got a system, there's lots of solar you're expecting to be charging, you'll come in here and you can see how the batteries are doing, all their individual currents. Just 2 weeks ago, I was charging a very large installation in a container. And, day after day, we were only seeing 80% state of charge. Couldn't figure it out. Was able to open up both the inverter interface and the link access interface. And that's when things started to become clear. So you'd see the charge controller say, hey, I'm reading the DC bus and I'm putting out 56 volts. You go to the batteries and they're saying, hey, my terminal voltage is only 55.
You got voltage drop on the bus.
So we were seeing upwards of 1200 millivolt voltage drop.
Oh, wow. Okay.
So charge current ground to a halt.
Yep.
So that's one way you hop in here and you can see live data
Yes.
just to verify. Also, you could go back and pull data logs from all the batteries just to piece together a longer picture of what was going on.
So you can see individual battery modules.
Yep.
Can you see strings within the battery modules?
You can. So we'll give you just minimum voltage, average, and max.
I assume there's more than one string. There might just be one string.
There's actually just one here.
Oh, because they're 100 ampere cells.
Yeah.
There wouldn't be room. Yeah.
Yeah, exactly.
I'm used to the little round things.
So we're going, the bigger is better these days.
Yeah, yeah. It's probably worth explaining that prismatic, in fact, I've probably got some on the shelf behind me here. They tend to be
the blue one right there.
Yeah, something a bit more like that is inside it. So that's 100 ampere.
Yeah, so this is almost, I'd say, the exact form factor. So if you were to picture it, if I'm doing this right, you'd have about 2 rows like that
Right.
stacked up.
Yeah, yeah. And they're welded together, whereas you've got cylindrical cells and then, of course, the pouch cells as well.
Yeah.
Yeah. All right. So, what's the advantage of using prismatic cells?
They're easier to assemble. So if you step back into our earlier products, there's upwards of 420 cells in a battery.
Yeah.
And it actually takes quite a bit of time to assemble that product. When you get into prismatic cells in these configurations, it's much quicker. It's all automated now. So all the welding's done with lasers. And you actually get more energy density. So you've got a lot of cylindrical cells. There's a lot of room, wasted space.
Yeah, like the curves don't really
it's
fit
kind of
together.
that area in between 4 cells.
Yep.
So higher energy density, more robustness, easier and more replicable in manufacturing.
Right. Oh, yeah. Cool. I was sort of wondering. Now, we've talked about closed loop BMS and the advantage of that in terms of very tight management, but you've also got something called active dynamic charging. Now, what's that?
Yeah, so we're running a lot of algorithms inside the link box here, or link 2. So it's always looking at all the batteries, the lowest cell, the highest cell, at temperature, and it's making decisions on what voltage it's requesting. So based on the condition of the system, it'll ask for a very specific charge target. So what you'll see is earlier on in the charge, that target is there to optimize the amount of power put out by the power electronics.
Right.
So if you're in an open loop system, for example, and you've got a more conservative charge voltage, what you see often is the power is throttled. It might be able to put out 200 amps, but it's only doing 80 because it's bumped up against that conservative charge voltage.
Yep.
So in that closed loop scenario, we can take that voltage target and raise it and pull that current up to its maximum potential.
Right.
So if you use bulk and absorption terms,
Yes.
it allows you to stay in bulk longer. So that's how you get a faster charge with active dynamic charging.
Yeah. So it's taking all the information like the cell temperature,
Yep.
the cell voltage, anything else?
Balance.
Yep.
So that's the key part. So when you exit your bulk phase and you get into absorption, that's where you really see the active voltage requests start to bounce around, and it's optimizing it for internal balance. So
At what sort of point do you transit to that balancing phase?
in truth, I guess the algorithm's always thinking of it,
Oh, okay.
but it really, you see its strength when the batteries are, they're taking in about an amp each.
Yep.
So
Because I've seen, some self-managed batteries, there's a request that they go through an equalization phase at least once a week to ensure that balancing does get to happen properly. But with dynamic active balancing or active charging, are you constantly trying to balance?
the balancing will be triggered at a certain point. So I believe it's 3.35 volts per cell. So as long as you're above that,
Yep.
you'll see balancing. But once again, it really starts to shine when there's a trickle charge. You're seeing about an amp per battery,
Yep.
and that's when the balancing really takes hold and is effective.
Yep.
So that's another benefit of open loop charging, or over loop,
Yep.
open loop. So in many cases with an open loop charge and more prescribed phases in the inverter, you'll see them walk through bulk, absorption, float. And they're going to make that jump from absorption to float based on certain triggers. And it's usually, call it a current-based trigger. So in an active dynamic situation where we have closed loop, there's no such thing as bulk absorption float. It's just hit my target voltage.
Yep.
Which means if we hit 54.4, stay there as long as you can, and the current will gradually taper. In an open loop system, it might be programmed to jump from bulk to float at 10 amps.
Yep.
So the battery's actually not finished balancing, but the power electronics have just moved to a float phase and charging's terminated.
Just to sort of explain it a bit more fully, these cells are connected in series, right?
Yes.
So one to the other, and each one's nominal, 3.2 volt cell, but you start to balance around the 3.3 volts per cell mark,
3.35?
3.5, but they don't all have to do it at the same time. That's the whole point of balancing, isn't it?
Correct, yeah. So you target the highest voltage, and we do top balancing. So you're trying to pull down that highest cell
Yep.
and allow the others to catch up.
How do you pull it down?
It's resistive balancing. So it takes a bit of current, turns it into heat.
Yep. Right. So there's a little bit of wasted energy in that balancing phase, but it's very small. It's like less than an amp.
It's a couple hundred milliamps.
Oh, a milliamp.
Yeah, so.
All right. Okay. It's really tiny. Yeah, cool. And in terms of the cell heating process, that's all automated, right? You set some temperature targets, so you've got some thermal sensors on the cells.
Everywhere. So there's a
Everywhere.
They're shockingly everywhere. On the
Yep.
relays, on the fuse, on the shunt.
On the relays.
Power supply, the cells.
Right.
Yeah, in the UL world, or if you're really looking at certifying a BMS, you need to be cognizant of all your critical temperatures.
Yes.
So I say the shunt because in our observations throughout the years, it's usually where the PCB is getting the hottest. So we've got thermal sensors around the shunt, and it's really to monitor the temperature of the PCB material and make sure it doesn't get too hot.
Yeah. Now, you mentioned UL. Which UL are these certified to?
So these are certified to UL 1973, IEC 62619 as well.
Both. All right.
Yep. And in UL 9540A and UL 9540.
Right. So that's the cell level 9540?
The 9540 is a collection of cell level, module level, system level.
Oh, okay.
So it walks up that chain. So you get a cell, you make sure it has 9540A.
Yep.
You go through the same types of tests and reviews at the module level. And then if we've got cabinets or systems, we'll replicate those tests yet again.
So for our Australian audience, what does this mean, having UL 1973?
Well, I guess it sounds like the equivalent is IEC 62619, but it's a requirement for our CEC applications here in Australia. And it's really just ensuring you've done proper due diligence in your system design.
Yeah. I believe you're in the process of getting that certified. So these should be available in the Australian market as CEC approved.
Yep. So we're expecting January here.
Yep.
So we're down to hang out with our friends DPA. They're assisting us in the CEC application. There are certain requirements for hosting documents and whatnot on local websites and having access. So working through the CEC application submission with our partner DPA.
Well, that's a good segue because I was going to say, where can people get these?
Yep, DPA is where you can get these, and if we should be ready to dazzle our audiences in January.
We've got Richard from DPA lurking in the background somewhere out here, probably with a big grin on his face right now. But that's great because I've had a long connection with DPA Solar. So, yeah, it's great to hear that. So will DPA be providing the support, or you do it directly through Discover?
Yeah, so we are in a terrible time zone to support Australians.
Yes.
So we'll be working with DPA Solar to ensure that we've got the know-how and the people in country to do what we call L1, L2 support. So that basic triage. And then
Let me guess, L1 is, have you read the manual?
RF, yeah. L1 is read the manual, please. L2 at times is also read the manual, but just more of an extensive review. And once again, if you really look at the failure modes of batteries, I'd say the primarily failure mode for a warranty, let's say, it's going to be around the cell. So beyond the cells failing or something going wrong there, the next failure mode would be the BMS. Now, we don't typically see those anymore with all our testing and verification. So that's a pure product failure or a warranty situation. And that might represent less than 1% of our service calls. The rest are typically configurations for inverters and systems. The wiring's gone awry, the settings aren't quite correct, which is also another benefit of closed loop because it takes away a lot of those failure modes of what was your charge voltage, what was your discharge cutoff. So yes, we'll be endeavoring to ensure that we can support the market the best way we can with DPA.
Now let's talk a bit about how that closed loop integration would work. You have probably a list of inverters and charge controllers that you already have integration with.
Yeah.
Let's say a new one comes along. Does it mean they've got to buy a new battery?
No, so we can actively update the closed loop protocols in the link here.
Yep.
And it's a quick field deployment of firmware update. And really, there's two ways of doing it. We've got our own protocols that are open and available online. And you do see instances where power electronics companies will take those and they'll deploy them on the inverter. But likewise, if a communication protocol is well documented and we get the right access to information, we can deploy a new closed loop integration in a matter of days.
Wow. That's impressive.
I'd say hours, but you got to always test. So
now, putting my installer hat on, so some hot tips for installers installing your battery. What are the sort of things to think about?
Hot tips.
I mean, in terms of one of the most common problems I hear and experience myself is making up the communication cable. The pins are different on either end. Maybe they're RJ45 connectors.
Yeah.
Maybe they're just terminals. You get your A and B around the wrong way. Those sort of things.
The first thing that popped to my mind was just cable cleanliness.
Cable cleanliness. Okay.
So we provide all the cables, and we've made this incredibly easy. So you're not making your own RJ45 cables. They come in the box. They're just standard. So one module to the next. Your DC cables come. So we've done our best to ensure that this is the easiest system there is to deploy. Almost no thinking, but that might be a dangerous thing to say.
So it's effectively a pre-assembled solution.
Yeah.
Yeah, and all the installer's doing is plugging it in. Now, when it comes to connecting to the charging source, of course, there'll be a variety of ways of that connection being made. Is that well documented? Like, is there going to be special pinouts, or you make adapter cables? Or
That's a great point. So for the home run cables, as we call them,
yep.
you've got your landing points within the box. So the installer will have to make those cables.
This is the DC bus.
This is the DC bus.
Yep.
Now, when it comes time to connect a closed loop communication, each one's well documented. And we take pride in having, we strive to have the best documentation in the industry. But the lid actually comes off, and the CAN pins are all configurable.
Oh,
so no more do you have to try to make custom cables, and it's a nightmare.
Oh, that's great.
You just pop the lid off.
Yep.
And each document will guide you on where to place the jumpers, and it's just a simple RJ45 connection.
Because there's two types of installers in the world: those that can make RJ45s and those that can't. It's like, damn, it doesn't work.
Put me in the can't camp.
Great. Well, I'm pretty excited. I'm like I said at the beginning, I've had a bit to do with AES, and I'm familiar with some of the other battery products. But I must admit, I do love a rack mount. It's just so space efficient.
Yep.
Using regularly available cabinets, or as you use your own bracket system. It looks great. I love the thermal management. That's a standout feature for me in this cold climate. And the fact that you've got a whole level of monitoring with the Link 2 really, just tops it off. So well done. So Brendan, I believe AES have been in Australia for quite some time.
Yeah, we've got quite a few deployments here with the 4248 series. I believe some of our earliest going back to perhaps 2017, 2018.
And where were they deployed?
A lot of systems in Western Australia, as I understand it, helping with some of the remote power sites and single Earth return systems here in Australia.
Yeah, they're a little bit of a weird one. Yeah, it's TWR. Yeah.
yeah. So really, the AES, I wouldn't say it's a new product. It's more of just a really great product enhancement. A lot of learnings and a lot of hard work going from our original product to what you see here now.
Now, we talked about integration with other charging sources. Do I have to sort of like custom integrate each time I connect to a different inverter or charger?
No. So while you can use our open protocols and integrate yourself if you have the capability, you would just connect to the Link 2 here with Link Access, go to the configuration tab. Well, that's battery configuration, sorry. And there's a preset list here. So
wow.
So you've got our open protocols, CAN open, serial CAN. Then you've Schneider BMS, SMA, Solar, Studer, Victron.
Oh, Morningstar.
Zambus. Some Morningstar work as well, yeah.
I just had the Genstar, had it on my channel recently.
Oh,
so
okay.
It's got CAN, so I guess you can chat to that.
We're integrated there as well.
Yeah.
And this list just keeps growing and growing.
Right. Okay. So it can be very simple. It can basically just open up the app, select the one from that drop-down list, and you're ready to roll.
Yeah, so you'd open up, select, save, configure.
Great.
Easy as that.
That was super easy. Now, I'm just thinking a challenge here. Let's go for the 36 of these battery modules in a stack, all connected together, and I want to turn it on or turn it off. So how do we turn them all off in one go?
Yeah, so another great feature of the new BMS, there is a global off feature. Now, it's provided inside the combiner box here. Just one click, and it will turn on every connected battery or off. So it's both on and off.
So that you've got motorized switches in these. So the breakers turn on and off?
The breaker itself will stay in the same position, but we've got two internal contactors, so they'll open up.
Oh, okay. So you'll hear a clunk.
Yes, yeah.
Right. Oh, that's great, especially in an emergency. You don't want to be running around trying to find all of the battery modules because they might not be in one stack.
Nope, just one click. To speak to that, we also have other heartbeat features, so you can integrate a little mushroom switch or what have you with the Link 2, and the Link will send a heartbeat, and if there's an emergency, you can interrupt that heartbeat, so the batteries will just turn themselves off.
Right, so they could be mounted external to the building, for instance, that someone can operate it remotely.
Exactly, yeah.
Right, oh, that's a cool feature. Now, speaking of remote operation, can you do it through software?
You expand on that, actually.
Like, from the app, can you turn off the batteries?
No.
Oh, okay.
So,
right.
it's a great feature. You can technically, but no, the user interface isn't there.
Oh, okay. All right. I was just thinking you might be able to identify a problem remotely and just shut them down.
Can I do that? It's possible. It's just the user interface isn't there.
Let's call that a feature ad.
Yeah. Add that to the list.
Yeah. Especially in a sort of a site that's there's nobody there. You know?
Yeah. So if you have larger sites like that, they're usually done by companies that have some kind of PLC or engineering team.
Yeah.
So through some of our closed loops, you can actually do that. You could send shutdown signals. You can take control of the heating yourself. So there are extensive controls for engineering firms and larger companies that want to have more of the control over their EMS.
Cool. Okay, that's it.